computer. Okay, so let's welcome Job Feldbrugge and welcome you all to take part in the fourth Gauge Gravity by the Ghat seminar. This online seminar series will focus broadly on the diverse topic in gauge and gravity theories. These seminars are roughly held twice a month, and we try to do it usually on Wednesday afternoon, and they bring together experts in the area of gauge and gravity theories. These talks will be recorded and they will be later uploaded in the CHEP YouTube channel. Some instruction for the audience is that just to stay muted during the talk, and if you have any urgent question, just raise the hand or type it in the chat box, and then we will just read it up and communicate it to the speaker. And today's speaker is Job Feldbrugge. So he is currently a Higgs Fellow at the Higgs Center of Theoretical Physics in Edinburgh. So previously, he had a joint position in Perimeter and Carnegie Mellon, and he did his PhD with Neil Turok at PI and Waterloo University. So he'll be talking to us on complex classical paths in quantum reflections and tunneling. And let's welcome Job. So yeah.
Thank you very much for the invitation. It's a pleasure to be here, even if only remotely. So, as Karov just mentioned, I will be talking about complex classical paths, Lefschetz theories. Ultimately, the goal is to develop this for the path integral of gravity. So I will talk a little bit about that, but I mainly will be talking about quantum mechanics, because I feel like we can understand quantum mechanics a little bit better and hopefully apply that to quantum gravity. And that way we can build some intuition and some mathematical techniques, which we then can test and then subsequently can apply to realms in physics, which are a lot more difficult to test. So this is work which I did with Neil Turok, a little bit with Jean-Luc Lehners, who is joining us for this first part of this meeting, I've learned. Weili Pen, who is jointly in CETA in Canada and in Taiwan, in Cynthia Academia, and Dylan Joe, who is his PhD student. So if there are any questions, please ask them during the talk or after the talk. I'd rather have something clearly explained than completely my talk finished, if that's at all possible. So the path integral. The path integral is maybe the most universal, most elementary, most elegant way to describe our universe. So it's amazing how successful it has been. So here you see the path integral for the standard model, or maybe also part of the full gravity, you can argue that. And the basic idea, which Feynman basically developed following Dirac's early work in quantum mechanics, is that the amplitude, so basically the square root of the probability for physical amplitude to go from A to B, from one state to another state, is simply, I say simply with irony, it's simply the sum over all phases of all configurations in which the particle can go from A to B, or the state can go from A to B, or the universe can go from A to B. So it has been said that the universe or the particle is a free spirit because it tries all the different ways out, and you sum over all these ways, and miraculously, out of all this incredibly complicated sum of this infinite dimensional space, you get this quantum amplitude, you square it, and you get a probability for some physical phenomenon to happen. So that's generally the idea. However, this integral is deceptively complicated. So it looks simple, but it is actually very complicated. So the first thing to notice is that it's an infinite dimensional integral. And that's something we can deal with, and which I will talk about more during this talk. Because the space of paths is infinite dimensional. Another problem is that it's only conditionally convergent, something also we'll talk about. But the main point is that if you take the modulus inside of the integral, you see that e to the power I, a real number, has modulus 1. So you integrate of something which, if you would put the modulus inside of the integral, would diverge. So that's known as a conditionally convergent integral, which is mathematically really tricky and in many textbooks even avoided. So the convergence of this integral has to do with very delicate oscillations. So you have to add and subtract different terms, and in this cancellation of all these terms, do you get your amplitude? One thing which I didn't include in this formula is the measure. And that's actually crucially important and something I will talk about at length. So the path integral for gravity was first envisaged by Wheeler, who said, well, let's consider classical particles in quantum mechanics as trajectories in space, and let's generalize that to general relativity and quantum gravity. And what he basically envisages is that you can start from one tree geometry and go to another tree geometry. And what you have to do is you have to consider all spacetimes which interpolate between these two tree geometries. And the path integral of these spacetimes would then give you the amplitude in quantum gravity. It's a beautiful idea. It basically connects quantum gravity to classical gravity, up to, of course, several problems like the problem of the emergence of time, but let's not talk about that now. So that's the idea. So this is this path integral for gravity. So you consider all initial, you start from an initial position, you go to a final position, and you consider all spacetimes in between, and you integrate over these. You also have an integral over lapse, which will come up, which is basically the time it took to go from A to B in some vague notion of sense. And that's the way of quantum gravity I've been thinking about. Of course, there is a parallel way of viewing quantum gravity, which is through the Wheeler-DeWitt equation. But I won't really be talking about that here. So the ultimate solution to your path integral will be solving the Wheeler-DeWitt equation in a sense. But the merit of the path integral over the Wheeler-DeWitt equation, as I see it, is that when you solve a differential equation, you always have to set boundary conditions. When you do an integral, you don't have to do that. Of course, you have to integrate from A to B, but you don't have to set additional conditions at the initial state for your Wheeler-DeWitt equation. So that's the reason that I will mainly be focusing on the path integral for gravity and trying to see how do we actually define this and how can we actually make this into an operational tool with which we do calculations. So what is this path integral about? So let's go back to quantum mechanics or classical mechanics. And what you can do is you can say, well, I consider the propagator, the Feynman propagator, to go from x0 to x1 in time t. And now Feynman's insight is that you can write that as an integral of all paths going from x0 to x1 in time t. And for every path, you calculate the action, classical action, sometimes called, and you say e to the power I, that action. And by summing over all these paths, do you get your quantum amplitude. And if you now square that, you get a probability. The idea of this formalism is that the paths which will significantly contribute to this path integral are the paths in the neighborhood of so-called saddle points. And a saddle point is just a different way of saying a complex or a real classical solution. So the idea is that the paths for which this integral makes sense are the paths for which the variation of the action is zero, which is just the Euler-Lagrange equation, which is just Newton's law. So what the idea is to consider all paths which go from x0 to x1 and solve this equation of motion. And these would be the saddle points along which this path integral would have support. So that's the general intuition you normally get from textbook quantum mechanics. However, which of these saddle points should you include? So you can have real solutions interpolating between x0 and x1, you can have complex ones, and generally an infinite number of solutions to this boundary value problem. And then the question arises, which one to take? And another question is, it's very nice to do this in the semi-classical approximation, but how rigorous is this beyond the semi-classical approximation? Can you describe everything in the universe using these classical paths being real or complex? Or is it part of an approximation? Do you have to stop somewhere and have to say, well, now I've done the classical path, part of the path integral, and now there's something remaining. So these are all very interesting questions, which were already thought of by Wheeler and Feynman and people who worked on these problems around the same times. For example, the DeWitts. But these questions are still largely open. So to start off, let's talk about a few problems of the path integral. And interestingly, if in Feynman and Hibbs' famous book, which is the kind of the first textbook on path integral integration, they already were letting us know that they were aware of these problems. So in Feynman and Hibbs, you can find a sentence which says, "We feel that the possible awkwardness of the special definition of the sum over all paths may eventually require a new definition to be formulated. Nevertheless, the concept of the sum over paths likely like the concept of an ordinary integral, is independent of the special definition and valid in spite of the failure of such a definition." So Feynman and Hibbs basically say it's very annoying and maybe a little bit disturbing that we don't have a proper definition of these integrals, but nevertheless we will continue and make progress regardless. And this is something we have done to great success in physics. But of course, if you would like to now treat quantum gravity, it would be nice to have a solid foundation, because there it's more difficult to actually test these ideas. So another thing which I would like to mention is something Terence Tao recently said. And he said, well, this is a very famous mathematician. He said, well, the point of rigor is not to destroy all intuition, as some people often mention when they talk about mathematics. They talk about algebraic geometry, say, oh, all these definitions, what should I do about it? But Terence says you should, instead, it should be to destroy all bad intuition and clarify and evaluating good intuitions. It's only by a combination of both rigorous formal intuitions and rigor do we tackle complex mathematical problems. And I think by extension, also theoretical physics problems. So what are these problems? So the first problem, which I would like to at least mention, is conditional convergence. So conditional convergence is something I talked about a little bit, but now I will define it and give you exactly why I feel like this is a problem. So famously, sum can already be conditionally convergent. And what does it mean? Well, if you have a sum, which is the sum over terms AI, but whose sum over the absolute value diverges, you call it conditional. And these conditional sums are peculiar because they depend on the order of summation. So if you take a formal power theorem of the logarithm of 2, then you see the natural logarithm, and you see that it's this alternating sum. And if you now take the modulus, or you just replace the minuses by pluses, then you find that this sum indeed absolutely diverges. However, if we now take not the red, blue, red, blue, red, blue elements, but we take red, blue, blue, red, blue, blue, red, blue, blue, and continue this way, in which the blues are the even terms and the red terms are the odd terms, then after a little bit of elementary algebra, you can see that this is half the original sum. So you started with one sum, you reordered the sum, and you get half the result. In fact, you can prove that if you wake up and you want it to converge to pi, or you want to converge to any random number, you can develop a simple algorithm to basically reorder the sum in such a way that you get the desired result. So the ordering of summation is really important, and that should be taken as part of the definition. And that's something which is very peculiar, because if you calculate the mean of your grades, then you never have this phenomenon. It doesn't matter whether you first take English and then take math, where you interchange the sum. But this is a very peculiar phenomenon which happens in conditionally converging sums. And the same thing occurs for integrals. So if we take the most simple oscillatory integral, which is the Fresnel integral, which is this integral. So we have e to the power I x squared. So you should see it as the sine of x squared plus I, the cosine of x squared. Then you can typically define that using a partial integral, and then you take the limit to infinity. And if you now take this partial integral, you evaluate it, and you get this error function. And if you go to the mathematics, or you ask Mathematica, or go to one of these textbooks on special functions, and you find that you arrive at 1 plus I, the square root of pi over 2, which is fair enough. That's very good. So you have taken the ordering to be a symmetric box, which should then have grown up to infinity. And that's kind of a natural definition, because you have taken it to be symmetric. However, if we now go to a higher dimensional situation, things become a little bit more tricky. So if you take n copies of this integral, so you take the product of them, then one thing you can say is, well, this integral factorizes. So I just take this number to the n power. So that's something you would like it to converge to. However, you can also say, well, the product of exponentials is equal to the e to the power I, the sum of the exponentials, which is like a radius squared. So the integral tempts you to do a spherical regulator. So instead of having a cubic box, which you drop to infinity, you can take a sphere, which is just as natural. However, if you now do the integral, then you find that indeed for n is 1, you get the desired result. For n is 2, you find something which oscillates around the desired result. For n is bigger than 2, you find something which diverges. So again, you see that the order of summation is important. So if you take a different regulator, you get a different answer, which is very annoying because in physics we have oscillatory integrals everywhere, which are often conditionally convergent. And so they are subtly dependent on the regulator. So why is this? Well, again, you can say that an integral is given by this thing, and it's only conditionally convergent. It's absolutely convergent if the absolute value converges, but it's conditionally convergent if this second condition is not satisfied. And that's typically the case for Fresnel integrals or for path integrals. If it's absolutely convergent, so if both these conditions apply, so if the integral defined in this way actually converges absolutely, you can use Fubini's theorem, which says that if you have a two-dimensional integral, it doesn't matter in which order you integrate, which is actually basically the reason that the two-dimensional Fresnel integral gave us this kind of trouble. And moreover, what you can prove is that the dominated convergence theorem applies. And the dominated convergence theorem is a very fancy word of saying that you can interchange the limit with the integral symbol. So if you have an integral, a family of integrals, and you take the limit of them, and you can move the limit inside the integration, if and only if, for all Fn, you can develop a G which always dominates it, and which is itself absolutely integrable. So if you have a sequence of functions which is not absolutely integrable, then you cannot find a dominating function which is absolutely integrable, and taking the limit inside is actually not allowed. So you can work out very simple examples where you basically get two different results. If you integrate first and then take the limit, or you take the limit and then you integrate first, you integrate subsequently. And these subtleties are really important for the path integral. So that's one of the problems. Another problem is that we are integrating over an infinite dimensional space. So in order to understand this, we have to do a little bit of integration theory. So if you pick up any book on integration theory, then you will find a definition of a sigma algebra. The sigma algebra is nothing more than a subset of spaces. So if we take R2, then we want to have all kinds of patches of R2. And what you say is that a sigma algebra is this collection of patches or subsets of my bigger space, if and only if the whole space is included, which is a very simple condition. If there is an element in a subset in this algebra, the complement is also in the algebra. So, for example, if the whole space has to be in the algebra, then the empty set also has to be in the algebra. It's also something which is not so difficult to engineer. And moreover, if you have a countable set of subsets, then you want the countable union of all these subsets to also be in the algebra. And this is kind of important in order to allow you to do limits, because you would like to take limits over all kinds of subsets in order to define your integral. And then it's important that it's actually part of the algebra. So given this sigma algebra, which is mathematically a very elementary construct, you can define the so-called sigma measure. So a sigma measure is nothing more than a map from this algebra to the set 0 to infinity. You can generalize this also to complex numbers or signed measures, but that won't be necessary here. So it's just saying what is the size of one of these subsets. So the first condition a sigma measure has is that the empty set is measure 0. And it's very natural, because if you would like to integrate over a set which is empty, you definitely want the integral to be 0, so the measure also has to be 0. The second condition of the Lebesgue measure is a bit more tricky, and that leads to some complications. So what you say is that if you have a countable set of subsets which are pairwise disjoint, meaning that if you take two of them, they never overlap, just like here, this A and B. These are pairwise disjoint. if we take the countable union of these pairwise disjoint sets, which is this thing, which is part of the algebra because of condition 3, then you can calculate the measure of it, because the measure is a map from the algebra to 0 infinity. And what you require is that the measure, the size of this joint set is equal to the sum over its components. So here you can also see why pairwise disjoint is important, because otherwise you would double count things and this won't apply. But this second condition is crucially important to have an integral and work with integration and use integration techniques like a Cauchy's theorem, which we will do.
Job,
Yes,
there's a question by Sumati in
Sure.
the chat box.
Yeah, I mean, maybe I can just sort of state it, just that if you're looking at the path integral, because, I mean, then really what you have, if you think of e to the is as the measure, right?
yes,
Then this is a complex measure. So many of these convergence conditions are not as simple as for a real measure. You have to
yes,
think in terms of, for complex measures, you have to think in terms of vector measures and so on. So
I agree.
conditions for those are very different. So I was just wondering whether that's also, yeah, just yeah.
So it won't be crucially important here, but I can say something about it. So when you have this measure, then you can also make a signed measure, so that allows you to go from minus infinity to infinity. And basically the requirement is that you won't take infinity, minus infinity plus infinity. So you are not adding infinities. But apart from that subtlety, it works, carries through. And then often what people do is they define complex measures, where you basically say the real part and the imaginary part are signed measures. So you basically have 4 copies of this ordinary sigma measure, and these constitute these complex measures. But I completely agree that the literature and the techniques developed are completely sound, but I just wanted to keep things minimal here.
Thank you, thanks.
But they are very relevant to quantum gravity. I completely agree. Okay. So if we have this sigma algebra and this sigma measure, what we now can do is we can define integrals. Finally, we can talk about integrals. So what you do is you first say, I make a simple function, which is basically just a block diagram. So when you first learn to integrate in primary school or secondary school or university, wherever you learned it, you often first say, well, it's the area around under a curve. But if you now have block diagram, then the area is really simple. Because you say, well, if the function is this kind of step function, then you say the integral over it is just the sum of the heights of these steps times the measure of these steps. So this is just the area law of a square, basically a rectangle. And now what we can do is we can say, well, let's approach this function, an arbitrary function, let's say a positive arbitrary function from below, and we can grow these blocks and make them finer and finer and take the infinite limit and then take the supremum of these, and that gives us a definition of this integral. And then you say, oh, I also would like to integrate over negative functions. Well, you say, well, I take my arbitrary function, I split it out in the positive part and the negative part. I do the integrals individually, and I subtract the two. Of course, assuming that not one of them is infinite, because then things become a lot more subtle. So this is the way integration theory is defined. And the sigma measures play a crucial role, because without the sigma measure, you cannot work through this construct. But now we can talk about infinite dimensional measures and show the problem. So this is well known in mathematical literature. In physical literature, is less well known. So the Lebesgue measure, which is the typical measure you use in integration of the real line or real plane, is defined in this way. So the measure of this subset AB is B minus A, which is just the length of this interval. And then if you go to Feynman and Higgs or any typical path integral book, then you say, well, the path integral measure, this curly dx, is defined as the infinite product of smaller x's. So what you do is you say, I go from A to B and I chop my path up into n steps, and then I integrate over all the intermediate positions, and that gives me my path integral. But in order for that to be formally an integral, this has to be a sigma measure, and it is not. And the easiest way to see this is that it is both both infinite dimensional and translational invariant, meaning that if I would take this interval and I shift it to the right, then the length is the same, so the measure is the same. And the same works for the n-dimensional version of the Lebesgue measure, which is just a product measure. But what we now can do is we can say, well, let's take the hypercube 0, 1 to the power n. And that certainly has measure 1, because you along every dimension you multiply by 1. The product of 1 to the n is 1. But what we now can do is we can take this hypercube and we can divide it in 2 to the power n smaller cubes. So you just cut that halfway in every dimension and you get these smaller hypercubes. But now, due to translational invariance, you can basically move them on top of the principal cube. So let's say the most left one cube. So the lower left corner, and you can move them all on top of there. So what you see is that due to translational invariance, you can say, well, 1 is equal to the measure of this hypercube to the n power is 2 to the power n of this smaller hypercube. But if you now take the limit of n to infinity, then a problem arises, because 2 to the power n goes to infinity and mu has to go to 0. So according to this very elementary algorithm, you can make it more fancy and more general if you like, but it already shows that the infinite dimensional measure, as taken as the product of these measures, has to equate to 0, which is very problematic and useless for physics, because now if you build bigger sets starting from these smaller cubes, then you get all kinds of crazy 0 sets, which is not what you want in physics. So the translational invariance basically is the problem for this infinite dimensional measure. So this is a problem for infinite dimensional integration theory. Luckily, mathematicians a long time ago have already figured out that there actually exist infinite dimensional integrals and infinite dimensional measures. This is often known as the Brownian bridge measure or the Wiener measure. So what you can do is you can use Bochler-Mindel's theorem, which is a fancy part of mathematics, which I won't really address in this talk. But you can prove that there exists an object which is an infinite dimensional measure on the space of paths, which goes from A to B for the Brownian bridge measure. So here you consider this set of paths, and you cannot really write it as a formal algorithm, so to say, but you can prove that it exists. Moreover, if you consider the subset of paths which go, for example, through these black windows, then you can calculate the size of this subset as this integral. And this is known as Wiener's theorem or Wiener's lemma. So there exists an object which is an infinite dimensional measure, and it cannot exist because it doesn't have a translation invariance. So since you pin the initial and the final position, that basically fixes the problem, because it's no longer translational invariant. And then you can do infinite dimensional integrals. And this is something which was done a long time ago by Katz, which was only a few years after Feynman's original papers. And this uses Wick rotation. So what Katz did is he developed the Feynman-Katz formula. And sometimes this name is used more conservatively, but let's here just be a little bit loose with the definitions and say, well, we have this oscillatory integral, which is conditionally convergent and then over the infinite dimensional space. Let's now do a Wick rotation. So we can let t go to it. And what you find is that the minus sign here becomes a plus sign and the I becomes a minus sign. So that's great, because now everything converges a lot more quickly and there are no oscillations anymore. But this thing is still ill-defined, because this infinite product of Lebesgue measures was ill-defined. And moreover, you can prove that the path over which a Brownian motion has support are non-differentiable. And here you take the derivative. However, as it turns out, the ill-definedness of the derivative and the ill-definedness of the measure here cancel, because together they can be assumed to be a physical realization of the Brownian bridge measure. So what you can do is you can say, well, this Wick rotated integral is ill-defined, but I can rigorously define it in this way, where you basically say that you have taken the kinetic term and the dx, and I have called it d mu. And this is Brownian bridge measure. Now you can integrate to your heart's content, and everything is mathematically well defined, and there are no problems, so to say, except for that you have done this Wick rotation. So this can be fabulous for many situations. But if you want to describe time evolution, and that's what I will be talking about in a second, it will be nice to take a little bit of a different route.
Job, there is a
Yes.
question question in the chat box by Karthik.
Yes,
This
this measures only for, sorry?
So I was just reading that question.
Yes, this measures only for free field theories in flat spacetime, right? Yeah, well, at the moment, this will only be for quantum mechanics. When you do field theory, it becomes a little bit more complicated. It can be done, but I won't really talk about that here. So this is just to show that the Brownian bridge measure has a use in quantum mechanics at the moment. All right. So how can we now do this same kind of tricks for quantum gravity or quantum physics, which is evolving in time? So this is the new definition of the patent rule which we are proposing. So when you take some mathematical physics course, then often you come across these oscillatory integrals, and then you do a WKB approximation or an Eichmann approximation. What you then do is you say, well, let's assume that only that the integral is only constructive interfering near the saddle points, and then do a Gaussian approximation of the integral around these saddle points. So what you do is you start with the integral, then you find a bunch of saddle points, let's say on the real line, and then you approximate this integral as sum over the kind of Gaussian approximations of these integrals, and then you obtain a sum which looks a little bit like this. And then you can be more fancy. You can say also let's include complex saddle points, but then which saddle points to take. And then the idea is normally that you start with your original integration domain and you use Cauchy's lemma or integral theorem to deform the original integration domain. And as long as you don't cross any poles, so you keep the endpoints fixed, you can obtain a set of saddle points. And these saddle points would then be an approximation of your integral. So this is what is traditionally being taught. But the key point to include to notice here that this is a local definition. So you have to locally expand around these saddle points. So what Pika-Lefschetz theory does, which has been addressed several times during this lecture series, is that Pika-Lefschetz theory managed to make this exact. So what Pika-Lefschetz theory tells you is that you can do a kind of a topological version of this saddle point approximation, where you start with an original integral, which needs to be analytic in order for this to make sense. And you can find the saddle points of the exponent. You can write it in terms of the real part and the imaginary part. And Pika-Lefschetz theory tells you that you can write this integral as a sum over integrals along the steepest descent manifolds of the relevant saddle points. And along these saddle points, the integral doesn't oscillate anymore. And the key point is that a saddle point is relevant if and only if the steepest ascent manifold of the saddle point intersects the original integration domain. So just to be really quick about it, so you take your integral, you consider your exponents, you calculate all the saddle points, you calculate all the steepest ascent and steepest descent manifolds, you then intersect all the steepest ascent, which are here the case, along which the integral would diverge. You calculate the intersection with the original integration domain up to some homological sense. After you have calculated the intersection, you know which saddle points are relevant. And Pika-Lefschetz theory basically tells you that you can deform the original integral in an optimal way to the steepest descent of the saddle points which were relevant. And along every of the saddle points, the integral basically converges like a Gaussian, often quicker than a Gaussian. And so it's exponentially suppressed away from the saddle points, and you get a beautiful integral which you can evaluate very easily. So in this deformation, all the work is done, and then subsequently the evaluation of the integral can then be done exactly. And this is not an approximation. You could make it an approximation afterwards, but it doesn't need to be. So what we can do is we can use this in a very simple setting and get a feel for it. So what we saw before is that you can do this Fresnel integral, and you can do that with this partial integral. But if you now take the limit to R infinity, then you basically follow this Euler spiral. And it takes a long time to converge, but at some point you will converge to the correct result, which is this blue point. So this is in the imaginary, the complex plane of the partial integral, so to say. If you do a two-dimensional version, as we saw, you can use polar coordinates, and you find something which doesn't converge, but it starts to oscillate around I pi, which is the result you would like to obtain. So if you now consider this integral, you can calculate its saddle points, which is at 0. then you can calculate the steepest descent manifold, because since it's already real, its steepest ascent will intersect the original integration domain. So you obtain a rotation by 45 degrees in the complex plane, and you integrate the Gaussian integral, and you get the same result. If you now take the two-dimensional version, then again you find the saddle point at 0, 0 at the origin, and it's the only saddle point of this very simple integral. What you find is that you have to rotate both the x and the y coordinates by 45 degrees. And after doing that, you obtain I pi, which is the result you wanted. So you see that using Lefschetz theory, you don't get all the oscillations, you don't have to take a limit, and everything converges very neatly. And what we have been doing, and I will be very brief here because I don't want to delve in all the details. I would like to rather like to see the applications. What we do is we say, well, if you have an n-dimensional integral which is only conditionally convergent, you can make it absolutely convergent by adding a regulator, GR. And this regulator is assumed to be analytic, meromorphic, as smooth as possible, and we will assume it to converge to 1 as r goes to infinity. So r to the infinity basically removes the integral. So here you say that you take the limit outside, and you cannot move it inside because it's only conditionally convergent for r is infinity by design. What we now do is we do the Lefschetz deformation of the original integration domain Rn for the f function. And again, we have assumed G to have no poles, no singularities at finite distance, which something you have to be very particular about. After you have deformed it to the steepest descent manifolds of the relevant saddle points of this function f, you can move the limit inside, because now it's an absolutely convergent integral. And what you find is that you take the limit inside and the G completely disappears. So you obtain the integral we were after, where you see that you can rewrite or define this conditionally convergent integral with the use of analyticity as a sum of integrals over this n-dimensional steepest descent manifolds of the relevant saddle points. And we propose that this is the integral we want to evaluate in physics. If you now extend this to the path integral for an infinite dimensional measure, then you have to do a little bit more work, but you obtain a very similar formula. So you find that this propagator, which was originally defined using this infinite product of Lebesgue measures, which is ill-defined, which has this kinetic term, which is problematic. You can rewrite that as a sum over the relevant saddle points, and then you obtain an integral which looks a little bit like this, where now this mu nc is a Lebesgue measure. Oh no, it's not a Lebesgue measure, it's a kind of a Wiener measure attached to every saddle point. So you find a set of relevant saddle points, and to every saddle point you have a steepest descent manifold, and to every steepest descent manifold you can define an infinite dimensional measure related to the Wiener measure, along which you can integrate. So this is a formal integral which is well defined in mathematical sense. And that's what we have been studying. So the key point in this definition, which you should take away, is that you have the equation of motion, you have the boundary conditions provided by your path integral, and you have to determine which of these solutions are relevant and which ones of these are irrelevant to either approximate or evaluate your path integral. And hopefully this formula will ultimately also apply to quantum gravity. And the key point is that an instanton or a complex solution to your boundary value problem is relevant formally, relevant to the integral, if and only if there exists a steepest ascent deformation of that saddle point to the real domain. So you should basically have a wire running from your space of real paths to this complex saddle point, which has to satisfy some properties. And this is difficult to implement, and it's something multiple people in the world are currently looking into, using either Monte Carlo techniques or analytic techniques. But that's the big puzzle. Which of the saddle points are relevant and which are irrelevant? And that's something where I will talk about a little bit more in a few slides. So this is the key formula we want to test. So let's first now apply this to the quantum Big Bang, which is the topic in which I learned about these techniques for the first time.
Job, I have a
yes.
question. So this formula that
Please.
you mentioned previously in the previous slide, so this directly follows from the Picard-Lefschetz theory, or there is some extra input that goes in over there?
It directly follows from Picard-Lefschetz theory, but you have to do some additional work. So the steepest descent
Right.
manifolds don't really generalize to the infinite dimensional case. So what we so it took us several years to figure this out. But what we now proposing is that you define some eigen descent manifolds, so to say, or eigenflow manifolds, which are in the same equivalence class as these descent manifolds, but it's not exactly the descent manifold.
I see.
So you have to do some additional work, and it's not pretty. And hopefully, at some point, someone comes around who finds a more elegant way of doing it. But this is the best we could at the time.
Yeah. Okay, thank
So
you.
that's also why I don't claim it to be absolutely rigorous. And this is still a subject where we learn new stuff all the time. But that was the goal, to make it absolutely rigorous, and we couldn't really pull it off, but we got a long way, we believed. So we thought, let's share at least how far we got.
Okay.
But all evidence in practical examples seems to go along these lines and seems to support that this construction will ultimately be able to be formally implemented. So that's also why I, in the abstract, say that it's an attempt or an approach rather than a full-blown definition, because there are some mathematical holes which are not completely fixed.
Job, there is a question
Yes.
in the chat box.
Can one check for a simple problem whether it gives better results than the saddle point approximation of the path integral? In principle, you can. You can using, for example, Monte Carlo integration, or you can use resurgence theory. So this is very much in line with resurgence. I will only talk about the saddle point here and already show you some surprising results which come from this formalism, which you would not obtain in the naive saddle point approximation.
No,
So,
my question was like, one can also systematically improve on the saddle point, right? Going to,
yes.
right? So
Yes, but you have to make sure that you do it correctly, because
this formula, no, if I understand correctly, you said that this formula is exact, right?
Yes.
But can one actually compute, like, for example, where your action is, let's say, not quadratic, but quadric or something, can one actually compute it? And I don't know whether this makes sense, but yeah. I mean,
so
like,
there are different
quadratic
levels
action,
of
course, you can solve it exactly. The saddle point solution is exact. But if you have a non-quadratic action, can one check that this one gives a better result than systematically improving the saddle point?
So I believe the answer is yes, but you have to be a little bit more refined about the question, because computation can be done in different ways. So you can do either a numerical Monte Carlo kind of evaluation of the integral along the thimble. So that's exact in a sense, but it's not a closed form formula. You can also do an asymptotic series. So you can take the higher order contributions of the saddle point approximation into account. But typically that will lead to an asymptotic series. So you have to Borel sum that. So it's not as simple as just integrating, because you can either do, for the Gaussian theories, you can do it exactly by hand and everything works, but nobody would be amazed by that because it's just a Gaussian theory. It's just a quadratic
even the saddle point is exact there.
Exactly. So that's kind of not a convincing proof.
Yeah.
If you have a theory which is not a quadratic theory, you can calculate the steepest descent manifolds, and you can do a Monte Carlo integral. And that's also exact, but in the Monte Carlo integration, you're always having a finite accuracy. But that's just inherent from that technique. So another way of doing it is to calculate all the order of the saddle point approximation. So we go to second order, third order, fourth order, and then you hope to converge, but then you find that it's an asymptotic series, so it diverges. And then you have to do some Borel summations in order to make this work. So it's something which people are studying a lot in resurgence. So it's an exact in some sense, but to evaluate it in practice, you have to do some more work, which I won't really discuss here.
Okay, thank you.
So I hope this is kind of an answer.
Job, there is a question by Karthik.
Sure. Where's the, yeah. I think it's the same question.
Can you hear me? Can I chip in?
Yes, please.
I don't understand what you mean by the formula is exact if it's not rigorous. Because you're telling us to find, a whole, like, suppose we're in the infinite dimensional case, which is the only place where this kind of, manipulation of measure theory is actually relevant. I mean, if you're in a finite dimensional space, it doesn't really matter. So we're trying to find, some sum over the relevant classical solution. And how big is that in an infinite dimensional space? And there's some contour in some infinite dimensional complex space, I'm assuming.
I agree.
So if this formula is not rigorous, it doesn't mean anything for it to be exact, because we don't know.
Well, I think the formula is rigorous.
Conditions are in an infinite dimensional space.
So I believe that this formula is rigorous, but it's difficult to completely, without any holes, mathematically prove it.
Okay, that's fair enough. I mean, yeah, I can agree with that. If you say if it's difficult to prove, but you believe it, I mean, that's fine. And then you also expect this to be some exact formula for what the path integral does.
Exactly. It would be the definition, so to say.
Yes. Okay. There's a slightly related question, if you would allow me. I thought it was known that the standard path integral, not this, redefined one, the standard path integral is known to not be a complex measure, especially when you have interacting fields.
Sure.
You're saying it would be a new definition of what the path integral means when the original definition is not valid.
Exactly.
Is that correct? Okay. So
yes.
Is there any calculation where this thing will give us a different answer than doing the standard path integral stuff?
So I will talk about it in a second. So
okay,
I propose you re-ask it if it's not I wasn't satisfactory after.
Yeah, perfect. Thank you.
All right. So in the remaining time, I see that I have still 14 minutes or something like that. Let's quickly go through a few examples. So one case where you actually don't have to do the infinite dimensional integral is the no boundary proposal. So this is the kind of context which I learned all of this stuff in, and was a big debate during my PhD on this topic. But since this is a meeting about gravity, I couldn't resist with putting it in. So this is work which I did with Jean-Luc Lehners and Neil Turok. So if you consider the path integral for gravity, and you consider a positively curved lambda-dominated universe, then Hawking and then subsequently with Hartle and Halliwell developed this beautiful proposal for the Big Bang, where you start from a universe with 0 size and you go to a universe with finite size, which classically allows space of the universe, and that would then be the mathematical model for the Big Bang. The beauty of this model is that in the saddle point approximation, there are no curvature singularities. So everything is well defined, and you might hope that the Einstein-Hilbert action might be enough to describe the fluctuations at the start of inflation, or basically resulting in the fluctuation seen. And the general formula of this integral in mini superspace, so assuming homogeneity and isotropy, takes this form, where you have this S, which is this formula, and then after a redefinition of the labs and going to Q is A squared, then what you find is that this theory is related to a particle in a linear potential. So here you have a kinetic term, and here you find the linear potential, and this is a path integral which you can do because it's a quadratic path integral. So you can do the path integral part of this calculation exactly, using, and you obtain an integral of this form. So you get an integral of the labs, which is like e to the power is0, which is the classical path, which is given by this formula. So you get this cubic in the exponential, and now you can apply Picard-Lefschetz theory. So what you can do is you can calculate all the saddle points, and you find that there are only 4 saddle points, so 1, 2, 3, and 4. You can calculate all the steepest descent and steepest ascent manifolds, which are all the j's and the k's. You can say my original integral ranges from 0 to infinity, so that's this line. And you can intersect that with all the steepest descent manifolds, steepest ascent manifolds, I mean to say. And then you find that only this saddle point has the steepest ascent manifold, which is the k, which intersects the original integration domain here, and the others don't. So you find that there's only one relevant saddle point, and you can indeed deform the integral to run along here. And you see that it goes from the green region to the green region, meaning that it converges. And then you can do the integral. However, what we found is that this was not a saddle point originally considered by Hawking. And in fact, if we go through the evaluation of the fluctuations, then you see why they didn't consider that to be the relevant saddle point, because it leads to the fluctuations to be not Gaussian, but kind of anti-Gaussian, so 1 over a Gaussian distribution. So you see that there is no minus sign here, which basically led us to say, well, if you take the non-boundary proposal at face value, and you don't add any additional terms, you don't try to fudge it, you're not trying to fix it, you are not putting anything else in, then it doesn't predict the Gaussian fluctuations which you use in the Bunch-Davies vacuum, but it rather predicts wild fluctuating spacetimes to be at the final time, which was the reason that we said, well, maybe this is not the way to go, and maybe you should consider different models. So this is something where we first applied Picca-Lipschitz theory, and you can see this formalism. However, since this integral is quadratic, you don't actually need to do the path integral over the path. You can do Picca-Lipschitz theory over the one-dimensional integral, which makes it a lot simpler. So let's now see this in action, where we actually have a theory where you cannot do that. So a very nice model, which is a toy model which has been studied before, but I think it should have deserved more attention, is the Rose-Morse potential, or also known as the Teller potential, partial Teller. And what you do is you say, I do quantum mechanics in a barrier or a well. So I will mainly be talking about the barrier, which goes like V0 divided by the cosine squared of x. And visually, it looks a lot like the Gaussian potential. So you have basically a Gaussian barrier or this V0 over cos squared barrier. And this is a very nice model because it allows us to evaluate everything exactly, using methods independent of path integration. So what you can do is you can say, well, let me consider this Hamiltonian operator. Let me consider the time-independent Schrödinger equation. And that's just a differential equation which you can solve. And it turns out that you can solve it in terms of these Legendre functions. So you find that the energy eigenstates of this Hamiltonian look like this. So you have some normalization factor, which is actually important. And you find the Legendre function of the tangent of x. So you see that as x goes to infinity, then this thing goes to 1 or -1. And you have these Legendre function, which like that because they are defined on the -1 to 1 interval. And you see that this n is a combination of -1/2 plus I nu. And nu is a function of the strength of the potential and h bar and the mass. Which is really nice. And this is a theory which has been studied and received a lot of attention in the past because for the well case, there exists specific configuration for which this well is completely reflectionless. Meaning that if you take any state, any package on the left and you put it towards the well, it will just move to the well and there won't be any reflection. That's the reason that this potential got a lot of attention in the 80s. But that's not why I will use it. So what you can do is you can say, given these energy eigenstates, I can generate the Feynman propagator using a spectral representation. So what you find is that you have these two eigenstates, plus or minus, corresponding to plus and minus momentum, basically. And you can insert them into this formula, and you get a one-dimensional oscillatory integral of the momenta. And if you do this integral, which you actually do with Picca-Lipschitz theory, it's not so easy to do, but you can do it. And I feel like we were the first to actually numerically implement it with modern computers to see what it looks like. You can just evaluate the propagator for this very simple model without any path integral techniques, without any saddle point approximations, and the result is exact. It's just a solution to the defining equations of the Feynman path. And what you now can do is you can do that for different times, for different initial and final positions. And what you find is that as a function of time, the absolute value squared of this path integral, this propagator, looks like this. And the real part looks like this. The imaginary part looks very similar. And what you see is that you have a structure like here. So you have a structure which is in this region, which is very striking. So this is the first time I've actually seen a propagator, a Feynman propagator, just as a plot, and see what it looks like and what kind of its features are. Yes, another question. Why is the spectrum continuous in K? It looks like the potential has bounded states. So if for the potential well, it does have bound states. For the potential barrier, it only has continuum space. So if the particle is not confined in any way.
But
that's why you have
X is for both plus and minus X, this cos S goes like exponential of X. So it will both sides, it has a bound, no? For X goes to plus infinity and minus both sides.
Yeah, that's basically just no, it goes like a free particle.
No, I mean, this potential looks like for large plus and minus X goes like exponential of X, right?
No, it goes to 0.
Why does it go to? Oh, it goes like exponential of minus X. Yeah, sorry. Yeah, thanks. Yeah. Yeah, sorry. Yeah.
So that's why you have a continuous spectrum.
Yeah,
if you have potential well, then you also have to consider the bound states.
Yeah, yeah, sorry, sure. Yeah, thanks.
So then you would have to include the bound states in this formula, which I've done, but I thought let's talk about the simplest thing possible. So the first thing to notice is that you have this peculiar pattern here. So there's an interference pattern there. And I have plotted these blue lines, and these are the so-called caustics. So this is something you know from optics, but it's also important in the path integral. So what you can do is you can say, well, let's investigate these regions. So let's say t is 10, and let's fix the initial position. So that's the horizontal axis, and vary the final position. So you can move basically from, let's say, from -5, and you can move along this line and see what happens. So if you start with your initial position at -5, that's this plot, and you go a little bit to the left. So you started off the left of the barrier and you move to the left of the barrier, then there's only one real solution to the boundary value problem. If you now slowly move the final position towards the barrier, then you find at some point that there are 3 solutions. So all of a sudden there are 3 solutions to the boundary value problem. And the movement from here to there is a caustic. And now you have the interference of these 3 saddle points, which you have to take into account. As you move the final position closer to the barrier, you find at some point that you have a situation in which 2 of these real solutions merge, and they merge here. Subsequently, you only have 1 solution to the boundary value problem. So it's not possible to go from A to B straight. You first have to go to the top of the barrier, and then you roll backwards. That's what you see here. And if you go to the right of the barrier, so you go from the left of the barrier, you go over the barrier, and to go to the right, and you find that you have to stick a little bit on the top of the barrier, and there's only 1 real saddle point. And these correspond to this behavior. So in this blue region, you have 3 real saddle points. You get an interference pattern, just like in optics, in wave optics. And outside, you have only 1 relevant saddle point. And you see that these interference fringes extend beyond the 3 solution region, which is the first signature for complex saddle points to be relevant. So what you find is that caustics are important, and they are not only important in the path integral, but they're also important in the solution of the Schrödinger equation. So if you have here an Gaussian state on the left of the barrier, which moves to the right, then you can evolve it in time. And you see that it bounces off the potential barrier. And it starts to oscillate because it's in a superposition of these 3 solutions. And you see that the region over which it oscillates is nicely bounded by these caustics, which are these green lines. So here you see it in the space-time image of this evolution of this wave package. And you see that it initially starts like a Gaussian, and it reflects, but the bounds of this interference pattern exactly corresponds to these caustics, which are the blue lines here, and which are the green lines here. So caustics are important, and that allows you to see how the saddle points move and how they interact. And now the next step I would like to make is that these saddle points which merged and disappeared from the real domain didn't really disappear. So what happened is they became complex saddle points. So here you see it for a very simple one-dimensional integral. which is known in catastrophe theory as the Percival interval, I believe. So you find you have 3 saddle points in here within the caustics, so 3 real solutions to your boundary theory problem. Then what happens is you cross the caustic, you see that 2 of them merge in common degenerate saddle points. And subsequently, you get 2 saddle points which are relevant, so the real one and the complex one, and an irrelevant saddle point. So you basically have 2 saddle points which coincide at the caustic, then become complex, and one of them remains real and the other one becomes incomplex. Another phenomenon which you know from optics is the so-called Stokes phenomenon, in which this complex saddle point turns off. So you see that there can be a situation in which the steepest descent manifold hits the other saddle point, and afterwards it's no longer relevant. So it has moved from a relevant complex saddle point to an irrelevant complex saddle point. And the same phenomenon can be seen in the path interval. So again, what we can do is we can start on the left of the barrier and we can shoot to the final position. And we can do that for all final positions and look at how these things behave. So if you only include the real solutions to the boundary value problem corresponding to real initial velocity, so this is the complex velocity plane, and these 1, 2, 3 corresponds to the domains in which these real saddle points live, these real solutions which you saw a second ago. If you now do the real WKB approximation, then what you obtain is that as h bar is decreased, you go to the semi-classical limit, and you get a good approximation of the exact propagator, which is here plotted in blue, within the 3 solution regions, and a reasonable approximation in the single approximation region. But you see that there are all these oscillations here, which are not captured by the real saddle point approximation. So what you can do is you can include these saddle points. So these live on these blue arcs, and these correspond to complex initial velocity, which still lead you to the real final position. And if you include these complex saddle points in the calculation, you see that you recover all the oscillations on the left of this caustic. You also see the decay comes in here. So the decay in the oscillations are a direct result of these complex saddle points, which are absent in this black curve, but they are present in these red curves, which are kind of the complex saddle point approximation of this problem. However, as you move and consider different configurations, the complex saddle points will migrate along these blue lines, and they will hit these points, these white points. And it turns out that what happens is that your complex path hits a singularity of the analytically continued potential. So your potential was 1 over cos squared, and this has singularities along the imaginary axis, and these complex paths can hit these singularities, and that's something I will talk about in the last minutes of this talk. So what you can do is you can now consider the whole plane of initial and final positions, and you can probe which saddle points are relevant in which configurations. And we find 6 qualitatively different regions. So you find that there is a region here, 1, which is also mirrored here, for which you have 3 real saddle points, and that's all you need. And then you have region 2 and 3, which also has a complex saddle points, which you have to include in order to get to match the exact result. And you find that there are also regions 4 and 5, and these will correspond to these singularity crossings, which I will talk about in a second. So basically, you can do a Picard-Lefschetz analysis based on the caustics and the Stokes phenomenon of your problem, of your classical theory, and that can teach you a lot about the quantum propagator. So the caustics are not only important in classical physics, but they are also crucial to understand the path interval, which I find fascinating. So
Yeah,
to close off in the last,
there is
yes,
a chat box.
yeah. Where were the blue lines in the plots in the previous lines? The blue lines, you mean these?
No, the one before this, the slide before this.
The blue lines here.
Yes.
These are just if you evaluate this interval. So the exact propagator.
Okay, and the red dashed lines?
The red dashed lines are the saddle point approximation using also complex saddle points, but only the ones which are relevant due to Picard-Lefschetz theory.
Okay. Thank you. Thanks.
So it will diverge at the caustics because there the saddle point approximation is useless. But away from the saddle point approximation for a small h bar, it does a good job, which is nothing more that you would expect.
Right. Got it. Got it. Thanks. Thank you. Thank you.
Sure. So just to close off, let's talk a little bit about tunneling and reflection, which was the title of the talk. So let's quickly go through that. So you can do the real-time propagator. We can also do the energy propagator. So for the real-time propagator, you have to include complex energies for the complex saddle points. For the real energy propagator, you have to include complex times. So what you can do is you can say, well, let me define the energy propagator by this path interval, which I say, well, let's not worry about infinite dimensional measures here. But so what you obtain is that you in the exponential, you have to add an ET, and you have to integrate over t from 0 to infinity. So for the path integral of gravity, that would be the integral of the lapse. And if you now look at the saddle points of this theory, then you find that you have the Euler-Lagrange equations, as always. But in addition, you get the Hamilton-Jacobi equation. And you require your solutions to your boundary value problem going from x0 to x1 to satisfy these conditions. And what you can do is you can calculate the exact propagator using this integral over the Jacobi, over the exact formula, which gives you the blue results. But you can also do the saddle point approximation for energies above the barrier, which give you the black dotted results. So you see that you don't capture all the oscillations on the left, but there exists a complex saddle point, which you can include in your calculation, and then you do recover all the oscillations. And this complex saddle point is thus responsible for the quantum reflection. So if your energy is above the barrier, you wouldn't expect any classical reflection of the barrier, but there exists a complex saddle point, and if you include that saddle point in your saddle point approximation, you recover the oscillations of the exact propagator, and you see that that's actually an integral part of the definition of the path integral.
Job, there is a question by Sanjeev.
Yes. If I understand correctly, you are still doing saddle point analysis, but using more saddle points. Is that correct, or am I missing something? That's exactly correct. However, in order to include these saddle points, I will have to analytically continue them beyond these singularity crossings. That's the next slide. So yes, this is only saddle point approximation, but in a subtly more nuanced way. So if you do this for the energy above the barrier, then you find that you include a complex saddle point for the quantum reflection, which turns off due to a Stokes phenomenon at x1 is 0. If you consider now the theory where the energy is below the barrier, then you find that on the left, the saddle point approximation using only the real saddle points does a good job. But on the right, it doesn't, because there's no classically allowed way to go there. However, again, there exists a complex saddle points which nicely captures the quantum tunneling. But again, you have to analytically continue them. So just to close off, what do I mean with analytically continue these saddle points? So if you would only consider saddle points which are just solutions to the equation of motion, as I said, then what you obtain is the green line here. So you see that you can capture the oscillations on the left quite reasonably. Then when you enter the barrier, you can still capture the quantum amplitude to a fair degree. But then at some point, you fail to find a solution. And what you do is you move the barrier, the final point to the right. You get these complex solutions, which you see here in brown and orange. But as you move the final position more to the right, these complex solutions will become more complex. And at some point, they will hit these singularities, these green points. So these are singularities of the analytically continued potential. And as you move through these singularities, you hit these barriers in this complex time plane, and you will have to analytically continue your saddle points beyond to a different Riemann sheet. And if you do that, then you do get a good approximation to your saddle point approximation, which is this red line. But only if you include these saddle points which are hidden behind these singularity crossings, behind these branch points. That's something we haven't seen anywhere else in the literature. So that's, we believe, a new result. In order to do the saddle point approximation correctly, you will have to consider complex classical paths which go beyond the singularity crossings, which can be behind branch cuts of your theory. This is still to be understood better, but as a final thing to say, what you can do is you can take this energy propagator and you can use that to calculate the tunneling rate, because the energy propagator is at x0 and x1 going to the left and the right, and you take the absolute value squared and you renormalize it with the square root of m. What you obtain is an approximation, or in the exact propagator, you get the exact tunneling rate out. But if you now do a saddle point approximation on your path integral, your energy path integral, and you do the same thing, so you square it, then you, to our big relief, you find that indeed you recover the tunneling rate of the WQB approximation exactly. But in order to do this, you will have to include you get a complex path which doesn't go from x0 to x1, but rather goes up in the imaginary plane, in the complex plane. So it moves along this path, which is a little bit disturbing because you don't go from x0 to x1. So you don't solve your boundary variable problem, but rather you are an analytically continued version of this saddle point. And you have to add a contribution to the action due to this singularity crossing due to this Brownian, which is of this form. And this is actually leads to the tunneling rate, which you would calculate with the WQB approximation, and explains the square root of V0, which enters there. So here you see in blue and red, you see the exact the tunneling rates calculated with the conventional methods and with the energy propagator. And in black and green, you see either the WQB approximation of the time-independent Schrödinger equation of the tunneling rates, or also known as the Euclidean tunneling rate. So that's the green one, and the black one is what you would obtain if you take your energy propagator, you do the saddle point approximation, including these funny analytically continued complex paths, and you square that. And you see that it coincides exactly. Actually, you can do the calculation analytically, find indeed these things are completely agreeing with each other. So you find that indeed there are complex saddle points, but they are beyond these singularity crossings, and they need to be investigated in more detail. So let's close off with that. So I hope that I've shown you some trouble and some problems which the path integral has, which I feel like we should resolve in order to do quantum gravity, because in quantum mechanics, we can just do the experiment and check whether our results are agreeing and whether we're allowed to do these mathematical manipulations. But for quantum gravity, we really should have a very high standard of mathematics, because it's so difficult to probe things experimentally. So I think there's a lot to be won by thinking more about the mathematical techniques which we do these calculations and define our quantum gravity calculations. Another thing I would like to mention is that Lefschetz theory could lead to a new definition of the path integral, where it's actually an integral. At the moment, only for quantum mechanics, so not field theory, but that's something I'm very interested in exploring. And finally, in order to do this procedure, you will need to analytically continue beyond singularity crossings when your potential has singularities. And this is something which needs to be studied in more detail. And if you would omit these terms, if you say, well, let's get rid of these analytically continued saddle points, and you just don't recover the exact result. So with that, thank you very much for your attention. I'm happy to answer any questions either now or by email. So thank you very much.
Well, thanks, Joe, for the wonderful talk. And now we can have questions. So I wanted to ask one thing. So in one of the slides, when you were mentioning about the singularities, so the singularities are they lying on, yeah, this one. So these singularities, are they lying on the same as your domain of integration, or is it like orthogonal? So this is, so these red and blue points that are mentioned in the first figure.
Yes. So these red and blue points are the saddle points as you move the x by the position. So what you do is you say, I fix my initial position, and now I will slowly change my final position to go to the right. So what you find is that if your initial position and final position are both classically reachable, you find two solutions to your boundary value problem. It's the green one and the blue one. So that corresponds to either direct propagation from A to B, or first you bounce against the barrier and you roll back. As you move the final position more to the right, these saddle points will converge at this green point, exactly when your final position is at the boundary, the boundary points, the place where the energy is equal to the energy of the potential. So that's the turning point. After you move beyond the turning point, these two real solutions become two complex solutions. So that's the orange and the brown points, and they will move in the complex plane as you move the final position further to the right. So these are these two solutions, so the blue one and the red one in this plot. And the point is that at some point, these solutions will hit this black line, this barrier. And if you now look at the solutions in the complex plane, then that corresponds to this solution, which hits this green point. And this is the real and imaginary x-plane. And this is the singularity of the potential. So what you find is that there's something very violent is happening. Your complex classical path is hitting singularity of your potential.
I see.
So it's a rather complicated plot, and I didn't want to. That's why it might be a bit confusing.
So we have a series of raise hands.
Yeah.
So first is
Yeah, I have a question. This so like for example, like usual way of doing this path integral is basically, okay, you solve the Euler-Lagrange equation, and which gives you the optimal path, and then it essentially gives the line of saddle points. So here, how do you actually determine the saddle points? Do you also still solve the Euler-Lagrange equation, which gives you the saddle points, or?
Yes, so here you can do it two ways. You can do it analytically, because this potential is so nice that you can find exact solutions.
Yeah, no, I'm saying that like cases where you don't have an exact solution, but
exactly. So what I'm here doing is for the energy propagator, I'm fixing the energy to be a certain number. And then you can say, well, I would like to solve the boundary value problem, but that's difficult. So let me solve the initial value problem for a time. So you fix the t, then you calculate the corresponding initial velocity, and that will be sometimes a complex number. And then you solve that, and you check where the final position is. So you just do a shooting routine. So you consider all kinds of different initial velocities or complex times, and you keep doing that till you find the solution to your boundary value problem. So just a shooting routine. And in order to make this plot, I have to do it brute force, do it everywhere. But in practice, you can use a Newton-Raphson method to. But the key point is that these complex saddle points don't appear at random. They are organized by these caustics. So if you know the caustics, which is something which is really easy to compute, you can have a fair handle on where these saddle points are living in your complex configuration space.
So another question, like, see, often like when you have these saddle points, I guess when it becomes singular, or when say two saddle point merge, something comes, there's some kind of phase transition, in the sense that like when you evaluate the action at that point, it shows some kind of discontinuity, either the first order or second order or something. Do you also see it here, like when your the saddle point merges?
The caustics, you mean?
Yeah, like when your saddle point merges and then becomes complex.
Yes.
At that point, do you see something in your solution, like some derivative diverges or something like that?
Yes. So in the saddle point approximation itself, or in the limit of h bar goes to 0, you find that the amplitude spikes to infinity. So that's a very definite probe. For finite h bar, you see that it's a huge spike. So it doesn't diverge, but it's just a huge amplification. So it's a little bit like looking in the sky and seeing a galaxy which is very far away because it's lensed and it's amplified.
Yeah, but like if you look at a not like second derivative or something of your solution, that also doesn't show any signature that your saddle signature of your saddle point changing. No,
not at fixed h bar.
Okay.
So what you can do is you can see how the amplitude changes as a function of h bar. And actually, Michael Berry has these beautiful, he calls it twinkling indexes. So these caustics basically tell you how it diverges to infinity. So if you calculate it at the caustic and changes the h bar, then you can determine with what kind of singularity it is or what kind of caustic it is by the scaling relations. But it's not exactly what you were asking.
Yeah. Okay. Yeah, okay, I'm not sure, but okay, thank you. Yes.
So there's no discontinuity at fixed h bar.
Okay.
Though in the subtle point approximation, things blow up. And the same applies to Stokes phenomena. At Stokes phenomena, everything is smooth, but the best you can do is that you say, well, the asymptotic expansion jumps.
Can I ask my question?
Yes, please.
Yeah. So in the kind of situation that you discussed, one can also imagine potentials where there are not just bound states, but also resonances that occur at positive energy.
Yes.
Now, how does the complex saddle method pick up information about resonances? Because resonances occur typically at positive energies. So how would you see, or maybe how would your formalism know about these?
I'm not quite sure. I haven't studied it in detail, but it's a very interesting question.
So, well, the reason I ask is because, I mean, the bound state problem typically is understood by looking at the scattering amplitude, and then you look at poles I mean, depending on how you, what your scattering amplitude is a function of E or P. The non-relativistic case, if it is a function of E, energy, then you look at poles in on the imaginary axis. But then you also have to be a little bit, I mean, to extract all the information, you also have to look at the second Riemann sheet and poles on the second Riemann sheet. And then there is a whole host of questions that appear there. For example, there may be bound states, there may be anti-bound states, and there are also resonances. And these are very much part of life, real life, so to speak, because we can do experiments and see
Sure.
these. But then the question is, in this method of complex saddles, even something as simple as two Dirac delta potentials, which are repulsive Dirac delta
Yes.
potentials that are separated by a distance. This is a nice example of a situation where there are no bound states, but there are lots of resonances.
Yes.
And so the question is, my question was, what would, well, I guess you have already answered it by saying that you haven't thought about it, but presumably the complex saddle point should have something, the complex saddle point method should have something to say about this, because if you shoot a particle at the right energy, then it will take a really long time to tunnel through and come out on the other side, and so
Yes.
on. So whereas if you shoot it with the right energy, it'll just go through the barrier as though it almost wasn't there. So
Yeah, I completely agree with you.
I was wondering if you had anything.
I have
to say
nothing
about
really
it.
new to contribute there. So it's just a very interesting question. I would love to combine these two fields and see how they overlap. And probably they have many things in common.
Yeah. I mean, I would imagine that the question of resonances would be sort of all pervasive, because they are definitely there in non-relativistic quantum mechanics. They're there in quantum field theory, and although I'm not a quantum gravity expert, I imagine that they would be there in quantum. There would be some version of resonances in quantum gravity too.
I agree.
Okay. Thank you. That was my question.
So there is raise hand by Karthik and Sumati. Karthik, do you want to ask something?
Sure. Yeah. I'm confused about all the complexifications that are happening. So we're considering a complex saddle point, by which I'm assuming it's a complex solution to whatever equation of motion we have. Is that right?
Agreed. Yes.
Okay, I'm fine with that. But then we're also considering complex time.
Yes.
But
only for the energy propagator.
But
So,
I mean, whether you consider a complex solution depends on whether the time is real or not, even in the quantum mechanics case. So what are we doing? Are we considering complex position solutions to the equations of motion with complex time?
So if you do the real-time propagator, so let me see what I can find in formula.
No, the propagator
so
is
if
fine.
you-
You can analytically continue the propagator in anything you want,
Yes.
basically. I mean, that's
Yes.
okay.
Sure.
But in the end, are we considering complex solutions in complex time?
Yes.
Or are we
So
considering
to answer this question, so let's first say that if you consider the real-time propagator, time is always real and a fixed number.
Yeah.
If you have a complex trajectory, then that complex trajectory have complex energy. Do you agree with that?
Complex energy defined with respect to the real time that you picked? Yes.
Yes. Good. So if you now consider the energy propagator, that's basically a Fourier transform of the real-time propagator, but now you have integrate over the time. And what
Real
happens
time,
is that yes, so now you fix the energy, and as it turns out, you have to consider complex time. And how you do this in practice is what you say, well, let me write my path.
No, wait. I'm already confused. We did
Sure.
the energy propagator by integrating over real time.
Yes, but
I
if you do
understand that.
Lefschetz theory on the integral over time, then we will
Yes.
find that there are saddle points for complex time.
Wait, what? Actually, am I the only one confused about this?
So I'm trying to explain how you actually implement it, and then I think it will become a lot more less
No. I did
confusing.
the integral in real time. I am perfectly happy doing integrals in real time.
Yes.
And I got some function of energy. Then what am I doing?
So you can either first do the integral internally here and then do the integral over time, or you can do them all at the same time. So if you do them simultaneously, then you will find that the saddle points include a complex t. And how do you actually define things then? Is what you do is you say, let me rewrite my action by a change of coordinates to have a path which goes as a parameter time, which only goes from 0 to 1. Let me add the complete duration of the time, be a free variable in my action, basically. So after a change of coordinates, you can basically get the t inside of your action as a parameter. And it turns out that that needs to be a complex number. So that way you can still define everything correctly and you can solve your equation of motion, but for complex t. And so what you find is that if you have the real-time propagator, you have real t and complex t. If you have the energy propagator, you have real E and complex t. I completely agree that it's a bit confusing, but that's how it turns out.
No, I mean, I'm confused to the point of just completely not understanding. That's my problem.
Sure.
What is okay, what are we complexifying? What are we starting with?
So you start with the space over real path and real time.
Okay, then what?
And you complexify both.
The real x and the real t?
Can I just make a quick comment, which I don't know if it'll help or confuse, but just to sort of ask whether, I mean, normally when we think of these things, we think definitely in terms of real position and real space, but real position and real time, but these are calculational tools, if you like, right? I mean, this is how we think the saddle points as contributions. So are you saying more than that, or are you, maybe that's something that, and I guess if you can complexify space and you can complexify time, to do the calculation, to estimate, to understand what is a dominant contribution from this particular integral, which is just just has two parameters in it, right? I mean, two variables in it, sorry. I don't know if that
Yes.
helps or confuses. Sorry.
No,
I think it
that is actually what I'm asking, because the position is a solution of the equations of motion, but the time is a parameter. So whether you complexify the solution or the parameter are very different things when it comes to quantum mechanics.
But in the energy propagator, you're integrating over both.
Okay, that's fine.
So they are on the same footing. So what symmetry, I think, says, and which I completely agree with, is that these saddle points are just a computational tool to evaluate this highly oscillatory integral. So there's nothing real to it in that sense. But it turns out that if you have a highly oscillatory integral, you can basically resum it to this complex saddle point.
And the saddle point is the sort of like a solution to the real equations of motion, or are you complexifying the equations of motion?
Complexified equations of motion.
That makes no sense. I don't know what a complex solution to the equations of motion is in complex time. I know what a complex solution is in real time, but I don't know what a complex solution in complex time is.
So after a change of coordinates, you can basically get the total time as a parameter in your equation of motion. So you solve your equation.
Just give me a simple example. Free particle. If I complexify the time and position, what is the solution to the equation of motion? Time is complex, position of the particle is complex. What the hell do I get?
Well, in that case, there's only one saddle point, and that's just the real saddle point you're used to.
No. Forget saddle points. I'm first calculating what the equations of motion and the solutions are. So in the equations of motion, when I take two derivatives with respect to time,
so everywhere you get a dt.
I use complex time, yeah.
So everywhere you get a dt, you get a 1 over capital T after the change of coordinates.
That is not an ordinary differential equation, because a complex equation is a PDE. There can be no solutions of that sort.
I don't know what to say to convince you at this point, but maybe we should.
No, I don't think it's about convincing me. I'm just asking you for an equation which has a solution.
Okay, so maybe we can just quickly first wrap up talk, and then we can continue the discussion. Karthik, is it okay? Sumati has a question. Sumati has a raised hand.
Yeah, so I just have a very quick question. It's somewhat naive, but see, all of these, I mean, all of this is just quantum mechanics, right, at this level. So,
exactly.
And this fact that you have these caustics and so on have to do very much with certain non-perturbative features of this, some sort of topology, whatever you call it, of the space of solutions, or, the contribution of this. So what I want to know is that, is this path integral formulation giving you more than just a simple Schrödinger equation? And is there, so in which case, with all of these tunneling solutions, I mean, we are familiar with tunneling solutions. We're familiar with reflections of barriers. We're familiar with all of that. Where do these caustics, I mean, are they just there in plain sight and we just didn't learn to think of them as caustics? Or what was it that, I mean, I'm trying to sort of see where the path integral in this formulation actually gives you, I mean, is it actually giving you more than what you actually have already with the Schrödinger equation? Or is it just one is being very, very careful with how we're doing that path integral? So very naive, don't mean to sort of push for more questions.
It's a perfect question. So this formalism gives you nothing more than the Schrödinger equation. And these caustics they're all alone. And they were noticed by Celine de Wit or by Schulman, who wrote a beautiful textbook about path integral integration, which includes them. But they somehow were never really popularized, so they were never really picked up. So there exist a few papers which discusses them, and Vladimir Arnold also worked on that. But somehow it never entered the the common discussion of path integral theory. So it's very puzzling. So you have books from the 50s which include this stuff, but then modern books don't include it. And if you just plot the propagator, then they're in plain sight. But it's very uncommon to just plot a propagator, because often it's a distribution rather than a smooth function, and it's difficult to plot. But for example, if you just consider the propagator for the well, so not the barrier but the well, then you get these kind of interference patterns. And if you give this to a radio astronomer, they will say straight away, oh, here I see the caustics, I see it running here, and I see one here. So they were just there in plain sight. And the goal of this project was to see whether we can understand the complex saddle points better, so that ultimately we can apply that to quantum gravity, where we don't know as well how things work.
Okay, so maybe I should at some point ask you for that old reference. I'm just curious. Thank you.
Please.
So any further questions? So we really had a very long discussion and interesting talk by Job. And Karthik has some questions, but in the meantime, probably we can first conclude the session and then continue further. And so let's thank the speaker again, and then we can stop the recording and continue with the session again for the discussion. So let's thank
Very much.
Yeah.
I think you're muted.
Oh, yeah, how to stop the recording? Let's see how to stop the recording.